Hi guys, welcome to Learn Electronics Repair, and I know some of you have been waiting for this video, so this is part 2 of the 12 most common faults or failings in electronics. What goes wrong, how it goes wrong, why it goes wrong, and what to do about it. I published the first 6 a couple of weeks back. I've been a little bit busy trying to get onto the second part, so here we're going to have 6 more. And of course that means we start with number 7. Resistors. Resistors come in all shapes and sizes. We have power resistors. We can see quite a few on this board. These big chunky things. We have all sorts of values from 0 ohm resistors up into mega ohms. And of course, on items like this, we have small surface mount resistors. The main point about resistors, although they are probably the most common electronic component, maybe also capacitors will share that crown, but the most important point is, generally speaking, they are very reliable. There are a couple of instances which I'm going to mention, but they are really very reliable things. And unless they are subjected to some amount of abuse, either electrically or physically, they're very unlikely to actually go wrong. So when do they go wrong and what happens with them? The 2 most important things about resistors then. When resistors fail, they fail by going high resistance. The resistance increases, sometimes to infinity basically because they become open circuit, but the resistance will increase when they fail. And I would say always. When you measure with a multimeter and circuit, you can see resistors, and you may find when you measure them, they read lower than the rated value. So for example, we see some resistors on this board here, and we see various markings. Now, it's important to learn these marking systems, because otherwise, when you were faced with a board like this, you would have to go and look up every single resistor to see what the markings are. And for example, that is not a 1001 ohm resistor. It's 100, and the last digit is how many zeros? 1 more 0, so that's a 1000 ohm. Yeah, this one actually here is 470 and 1 more 0, so 4700. Not 4,701. And you think, well, there's not much difference there, yeah? But there is actually a great deal of difference in some cases. Like this one here, 512. That's not 512 ohms. It's 51 and 2 zeros, or 5,100 ohms. So this is why you need to learn these. The only ones which are a bit more difficult are the ones like these, O1C. I normally loop these up because I'm not familiar with them. And it's not quite so easy to learn that one, that system. You'll probably get used to certain values after a little while. These are close tolerance resistors, okay, 1%. And you have to look these codes up probably. Look, one there, 183, not 183 ohms, 18 and 3 zeros, 18,000. And the same applies, of course, to resistors with color codes. Go and learn the color code system, guys. It will save you so much time, okay? Now back to measuring resistors and circuits. So we mentioned this one, 512, 5.1K, or 5,100. And this reads in circuit, if I can get a connection through this lack of coating on this board, well, it's reading open. Now that would suggest this could be a faulty resistor, because when they fail, they always go high. Let's look at this one, 5100. Yeah, 1 more 0, 5.1K. You see that reads lower. Yeah, 2.6. Can you see that? 2.63. That is not a faulty resistor. Resistors do not fail by going low in value. It will read low simply because there's something else in the circuit affecting the reading. So this one here, 2.5K. Now the value is marked at 4.7K. Again, that is not faulty. They always fail high. So we come back to this one, 5.1k. Either this is a faulty resistor or I have a bad connection against it. And really probably the only way to find out is to scrape away this horrible lacquer, okay? I've removed the horrible stuff. Let's try measuring this one again. And you can see it reads 5.11k. So it in fact is fine. The important thing here is do not be concerned about resistors in circuit that read lower than they should do, okay? When I say lower than they should, I do not mean if they read 0 like a short, because it's not reasonable really for a resistor to have a short across it, otherwise why have the resistor? About the only caveat to that is if it's got a inductor coil across it. Yeah. Okay, so that's how you should take readings on resistors and circuit and what they mean. So failure, well, the most common resistors to fail are either high value resistors, which go open circuit or higher than they should, and low value resistors, which tend to burn up. Yeah. The reason for that is low value resistors are generally passing quite a lot of current. They're low value resistors, and if they burn up, you can 99.9% of the time say they burnt up because something else failed, causing the resistor to pass too much current. That's why it burnt up. So resistors like these, if they're burnt, like these, if they're burnt or cracked or broken, yeah, they won't do that on their own. It's because whatever they're powering, in this case it is high powered transistors, have failed and gone short and taken the resistor with them. So that's what happens to low value resistors when they fail. High value resistors are a slightly different thing. High value resistors don't tend to burn up when something else fails because, well, they're high value, so they can't pass much current. But they do have a habit of just wearing out, can we say, just failing. And there's two very common places we will find this. One is in switch mode power supplies, and you will find resistors like these. So again, this is not 4703, it's 470 and 3 more zeros. So 470,000 in series with another one, another 470,000. So that's 940,000, almost a mega ohm. And you often find 3 or 4 in series, and they may be higher value than these, 1 meg or more. These sort of resistors and switch mode power supplies are part of the startup sequence, which powers the power supply up when you first apply the mains. And those resistors have a habit of just giving up. It may be intended almost a 1 mega ohm resistor, and it now reads 7 mega ohms or something like that. They don't fail by going low value. Like any resistor, they go high value and the power supply won't start. So that's commonplace. The other one, but this will only apply if you're working on vintage equipment with vacuum tubes or valves. Those circuits have a lot of fairly high wattage, often high value resistors into the hundreds of kilo ohms or mega ohms. And again, with age, they just tend to gradually increase in value to a point where the circuit no longer functions. So that case, high value resistors, they have a habit of just failing. And the other common failure with resistors is physical. Sometimes, especially surface mount ones, they just get broken, they just get knocked off the board. Especially in the case of boards like this one, a motherboard, or even more so a graphics card, where there are also a lot of components on the back of the board as well. If it's not been stored properly, it's been kept in a box or something, or suffered some other sort of abuse, you'll often find those sorts of small resistors just broken off the board. So that's the other most common place that you'll find faulty resistors. So just to sum up, resistors always fail by going high in value. When you measure them in circuit, they may well read lower than the rated value. This is normal. High powered, especially low value resistors, if they fail, burn up, that sort of failure, it will be caused by something else. So you need to find the cause, a short circuit. And high value resistors around the 1 mega ohm, especially in things like power supplies and the startup circuit, if they fail, it's probably just the resistor. Yeah, just change the resistor and it'll work. Okay, so I think that covers just about everything we need to know about resistors. Let's move on to number 8. And number 8 is Opto isolators. Inside the Opto isolator or Opto coupler, we have on one side an LED, an infrared LED, and the other side a photo transistor, or maybe a photothyristor or phototriac, something like that. Okay, and the way this basically works, if you want to send a signal from one part of the circuit to the other, whilst maintaining electrical isolation, so there's no electrical connection between the two sides, one way to do that is with an Opto coupler. We can see that clearly on this power supply. One Opto coupler, a big black line marked on this side of the board. And if we look on the other side, you'll see that this circuit is isolated from this circuit. There's no electrical connection between the two. Okay, so that is Opto isolators. What goes wrong with these? Well, the common failure here is that the LED inside this package loses emission. So with age, it just becomes fainter and fainter until eventually it can't shine enough infrared light on the phototransistor to switch it on. Or it may partially switch it on, but not properly switch it on. The way to test this is in circuit. Use a multimeter or something similar to apply a voltage in diode mode across here. Light the LED up. If the LED is intact, you should see 1.05 plus or minus a very small amount, but between 1 and 1.1 volts across it. That's the voltage drop of an infrared LED. Okay? If it's anything less than 1, you've got a problem somewhere, probably in the surrounding circuit, and if it's more than 1, you've probably got an open circuit LED. The other side is a phototransistor, and if you connect a multimeter again in resistance or diode mode across here and apply your other multimeter across here to light the LED, you should see the resistance of the transistor change. That's how you basically test them, but I have made a video, all you need to know about Opto isolators to fix stuff. I can link that to this one, or just Google for testing Opto isolators in circuit and you'll find the basic principle. So Opto isolators, especially in older equipment, are a common failure. If you're unlucky enough to have one that kind of works but doesn't work properly, you may well have to change it to prove it. Just get another one if you suspect it in any way. They're cheap and fairly easy to get. And the very high likelihood is that if you change it, you'll fix the fault. It probably isn't caused by anything. It's just caused by the fact that it's old and tired. So that's Opto isolators. Now let's move on to number 9. And number 9 is anything facing the outside world. Now, we talked about connectors and the problems we can have connectors in the first part of this video. I'm not now talking about connectors. I'm talking about the components that are connected via the connectors to something external. Yeah, that could be something like these type of connectors where the user plugs something in. Or it could be connectors like this, which are part of the assembled equipment. So they're not connected and disconnected by the user. Okay, this is from an air conditioner, so this is basically assembled. Now, you'll often find on the motherboard, obviously, a processor, on here a microcontroller. So this is a microcontroller, and this is talking to the outside world. It's receiving inputs from various sensors, for example, like a thermocouple or a humidity sensor, speed detection from a motor, whatever. Yeah, it's sensing the various peripherals attached to the board. And it's also driving things like switching on or off a fan or something like that, okay? Displaying onto a 7-segment display some sort of operational code or error code. So the processor itself is effectively insulated from the outside world, which means that if you have a problem with whatever this connects to, the chances are the chip which is involved in the communication is going to get it. Yeah, so common failure, especially with microprocessor control stuff, look at all the chips that are facing the outside world. And we can generally do this just by looking up the datasheet to see what the chip does. So for example, this one, CS2003. And here we have it, and you can see this is a 7-channel Darlington tube driver circuit, they call it. High voltage, high current Darlington transistor array driver circuit. And you can see inside there 7 of these drivers basically. So this is going to be controlling something external, a relay, anything else really you want to drive from the microcontroller would be connected to here. And we may find similar chips, latches and buffers and whatever, accepting signals coming in. Because these are connected, as I say, to something external, then they can be subject to a few forms of abuse. One would be some problem with the device that's connected here. Another one is just voltage spikes. This is coming down maybe long cables, lightning nearby, anything like that causes some sort of surge or spike. That thing is the first in line, yeah? It'll probably save the processor because that will just take the surge and die, yeah? But those type of chips are prone to failure. The only way to be sure probably is to just replace them if they're cheap and easy. You may be lucky and find the thing has a hole in it, something like that. You may also be able to measure from all the inputs to ground and all the outputs to ground and see if you can see one that reads different from all the others. You can't necessarily say what they will read, but they should all read the same as each other, depending of course what may be plugged in here. But in a lot of cases you can probably find one which has a defective driver in it. Bear in mind these things will normally have 4, 7, 8 drivers in one package, so the symmetry there's a number of the same and you can make a comparison. So things that face the outside world, inputs, outputs, buffers, latches, drivers, these are another common cause of failure. And on to number 10, glue. Yeah, glue. So you often find glue on PCBs, this white silicone stuff here for example. It's often there to hold heavy components down, basically to stop vibration and stress, G-forces applying to the actual solder connections, which may well break the connections. Dry joints, we talked about them in part 1. But glue. So there's 2 common types. There's this white stuff. This is like a silicone type rubbery stuff. In my experience, this doesn't fail and doesn't cause any problems. The one that causes the problem is more like this yellowish colour, or at least it is when it starts off, and especially due to age and heat it turns brown and then eventually to dark brown and then to black. Okay, when that glue goes into a dark brown black, it becomes conductive, and conductive means it can short things on the PCB. So any device that you see this old blackened or dark brown glue is a suspect. Yeah, really you need to get it off the board. So you need to get the glue off, which sometimes is easier than other times. It may have already caused a failure, so you may see burnt out resistors, blown transistors and diodes, burnt parts of the PCB where high voltages have arced through the glue. So glue is something to look out for, and as I say, especially the yellowy beige to brown coloured stuff. This sort, and there's a black sort which is rubbery like this but black, in all honesty don't really cause a problem. If the glue has become conductive, it can cause all sorts of damage to the PCB. So not only do you need to get the glue off, but you need to have a good look around to see what components in that area may well have failed. Or when I say in that area, components that are connected down PCB tracks to that area. Okay? On to number 11, varistors or MOVs, thermistors, NTCs, TVS diodes. Okay? The reason I group these together is because they are basically all protection devices. The NTC, and we have some here, but they don't have to be black. They are normally circular like this. It looks a bit like a large black capacitor, but they're not capacitors. These are devices that prevent too much current flowing into a device when you first switch on. So you're going to find these very near to the input of the circuit, usually before the bridge rectifier if it's a mains powered circuit. And these start off with a relatively high resistance, say 15 ohms, and then go down in value as they warm up. By starting at a relatively high resistance, they limit the current that flows into the device to charge, for example, the main capacitors. These therefore are subject to a fair bit of stress, especially for items that are being connected and disconnected from the mains on a regular basis. They will fail eventually, and they go open circuit. Sometimes they actually blow up, crack open, but they go open circuit. These do not fail in any other sort of way. So have a look for these, especially on things that will not power up. They're dead, as though a fuse is blown. This is blown. Okay, these can also fail for a second reason, and that is because there's a short circuit in the device. Quite often in the big switching devices under here, and that short circuit will cause a massive inrush of current when you switch on. Yes, there's a fuse, but the current is flowing through the fuse and through these things, and there will be one on here. This one's there, look, PTC. That's a PTC rather than NTC. There's one there, and all the current flows in that way. So depending on which gives up first, the fuse or the thermistor, one or the other or both will blow. Okay, so that's the other place you'll find these. If the thing is cracked, physically cracked and broken, the chances are there's a short somewhere that caused it to happen. If it's just gone high resistance or it's reading open, it may well just be because it was tired. Then we have MOV, metal oxide varistor, or sometimes just called a varistor. These normally look like this, so they're usually blue, don't have to be, but usually blue. Two wires again, it looks like a large disc capacitor. They do come in different sizes, of course, and these are protection devices again. So whereas the NTC or thermistor is generally there to prevent too much current when you first power up charging the capacitors, and it does so by starting at a high-ish resistance and going low, these MOVs protect against voltage spikes or surges. So these actually are a resistor whose value varies with the voltage applied. Basically, these are open circuit, they don't conduct until a certain voltage, and then they do conduct. They become like a short, kind of like a Zener diode if you like. But whereas a Zener diode is intended to regulate a voltage, these are intended to short out the voltage spike. And by doing so, if the voltage spike or surge lasts more than some milliseconds, these will just explode. So these normally fail by exploding. They look like capacitors, but they're not capacitors. They are MOVs, MOVs. Okay? If these fail, normally you may find the fuse blows because these became short. And generally speaking, these fail because of some external voltage spike. So usually just replacing them will fix the problem. If you're not sure whether your circuit has MOVs or NTC thermistors or both, it's also very easy to tell by looking at where they are in circuit. And I'll just show you where these are commonly found. Both these components are generally found on mains powered equipment, but they don't have to be. We can get MOVs that react to lower voltages, say 48 volts or above or something. So they can be on lower powered devices as well, or rather lower voltage supply devices. But generally speaking, you'll have your AC coming in, live neutral, often with filter capacitor, maybe filter inductors as well, maybe something like another filter capacitor, and then the bridge rectifier, AC, plus minus, and then we have our large smoothing capacitor or capacitors, something like that. Okay, the NTC would go here usually. Okay, it has a symbol like that, and you can see that is in series with the current that's coming in to charge the capacitor, so it limits the current. That's your NTC. And then the MOVs will go across here, quite often just on the input. So you'll have your MOV here, and again it has basically the same symbol, but it's wired across the mains. So this is a fairly low value resistor which decreases in value as it warms up, and this is an extremely high value resistor that becomes like a short circuit when the voltage exceeds a certain amount, and that will depend on the rating of the device. You can look up the part number. If this is exploded and you can't even read the markings, you can normally work out. So if you know the input voltage, you can usually work out a suitable component to go in there. And you don't put one rated at the input voltage. You'll often find for 220 volts, it might be 275 volts or even 400 volts, okay? But you can generally work out, or just ask around on the internet, on forums, what value you should put in there, okay? Normally they just sort of split open so you can actually read the marking anyway. Sometimes you might find something like this as well, that type of arrangement with two of them. Okay, so those are the MOV. There's a similar component to these MOVs, but used generally in much lower voltage circuits. And I'll just show you these because these are also a protection device which tend to fail on occasion. And that's these things. You may think they're diodes or capacitors. Sometimes they don't have a marking. They look like this. And these things are TVS diodes. So a TVS diode is basically the same thing really as a MOV, but it works on a much lower voltage and it's connected across the voltage input. This is a hard drive. You may well find a TVS connected from the 5 volts to ground, and the idea is that if you accidentally put 12 volts into the 5 volts due to an incorrect cable, this thing will go short, and they do go short. So TVS diodes go short. Usually you could just unsolder it and the device will work without it. Bear in mind you no longer have the protection. You don't only find these things on hard drives, you'll find them on a whole variety of lower voltage equipment, but this is a very common place to find these. So to sum up, the thermistor or NTC should read a relatively low resistance. The TVS diodes and the MOV or varistor should read open with your multimeter. They are protection devices. When they fail, they go short, apart from the thermistor which goes open. If you have blown MOVs, blown TVS diodes, probably just replacing it will work as long as you have got rid of the external voltage surge or incorrect wiring. They're there to protect everything else rather than cause other components to fail. With the thermistor, especially if they have blown up, it's caused by something else most likely, causing the device to draw far too much current. For example, short circuit in the outputs. Okay, so That is MOVs, TVS and thermistors. And so to number 12, firmware. And this is a problem that we never really had back in the day. Okay, this is more of like a recent plague. So modern electronic devices are usually microprocessor or microcontroller driven, and they have firmware. Sometimes in an EEPROM, this is quite an old one, often it's just an 8-pin chip. But that firmware is what controls the device. The firmware could be in the microcontroller itself, or it could be in an external chip, EEPROM chip. And the firmware can become corrupted, in which case the device will not work. It usually just won't start up. People can call this bricked, okay? And this can apply to just about anything from an MP3 player to an Android TV box to a television to an air conditioner controller, a motherboard, a BIOS. Graphics cards have BIOS or firmware chips on them. And this is where I would call it not a proper fault. So although the device won't work, you cannot diagnose and repair this by poking around, even knowing what you are doing with your multimeter. Because at the end of the day, there is nothing wrong, really. All the components are okay. It's just the contents of the EEPROM or the flash memory built into the microprocessor, microcontroller, that's faulty, it's corrupted. It could be corrupted due to user error. For example, people trying to flash a device, update a BIOS, something like that, and they put the wrong firmware in, or something happens during the update where the power goes off, you have a power cut, things like this, and you can easily enough end up in the situation where the thing will no longer work. This can be very difficult or impossible to repair, because there's no point replacing the component with a new blank one, because it's not the component itself that's faulty. You probably need to remove, in the case of an EEPROM, the chip from the board, get into a programmer, have a look online, ask around. Maybe you need to find another device of the same type and remove that chip. You're going to need an EEPROM programmer, often more than one, because some programmers will do some things, others will do other things. There are some very esoteric programmers like this one. This is a Virtunoff jig. Okay, Virtunoff jig. Some of these things are very hard to get, and you need these to program certain types of devices. This is a whole topic in itself, and it requires some specialist knowledge. You can learn it, we can all learn it if you have the kit, and you can get the firmware files, and you know how to program the device. Maybe you can restore it. Sometimes it's just a matter of disconnecting the battery. On a laptop, for example, a lot of laptops will fail, it won't start up. Disconnect the main battery, which is usually inside the thing these days, take it apart, get the battery off, make sure there's no CMOS battery, leave it for 10 minutes, put it back together, it will work. Yeah, that's because the firmware in the EC chip, which is responsible for the startup, got corrupted, but it can kind of like sort itself out. It's more like having bad CMOS settings, really, like resetting the CMOS on the motherboard. You're not reprogramming it, it's just corrupted settings that stops the thing from booting. That's what this thing is for, by the way. One of the uses is to actually program EC chips in laptops, which it does via the keyboard connector. Also, we have firmware in TVs on the T-Con timing control board. This will also program those. So, as I say, it's a specialist topic, but it's becoming more and more common these days. If you suspect corrupted firmware, then I suggest you get into the various repair communities, ask and see if anybody can help you. Maybe, once you're expert enough, you can help other people. Okay, so firmware, that's number 12. And now a little bit of bonus material. Number 13, yeah, unlucky for some. But very common failures. So I'll just mention these. One of them is in switch mode power supplies. This is one embedded into this board. This generates the power supply for the microcontroller, and for the relays it gives 12 volts and 5 volts out. And you will always find in these circuits on the output, this is the low voltage side, a diode like this. So this is the rectifier diode converting the low voltage AC, high frequency, coming out of the transformer into DC to be smoothed by the capacitors. These are a fairly common failure. Always worth a check on a switch mode like this is the diode short. They don't have to look like that. They commonly also look like this, okay? This type of diode. Also commonly look like this. This is a diode look, D101. And they can also look much larger. You see? A diode. These are dual diodes. So there's two diodes in the package. We have some slightly smaller ones there. We have some on heat sinks. Okay. Another one here. You can see the two diode symbols on that one and on that one. So these are diodes you commonly find on the output of a switch mode power supply, and they are a common failure point. Sometimes due to short circuits on the output, but sometimes they just give up. And the last bonus one, we'll still call it number 13, why not, is something you will not find on a PCB or on the device, because the other number 13 is the customer, the owner of the device. They fail on a regular basis. Sometimes they fail to tell you what they've done to the device. Sometimes they fail to describe the fault properly. And sometimes they fail to the extent that they actually bring you a PCB that there's nothing wrong with, which they insist is faulty. So, faulty customers, yeah. This is kind of like 6 of one and half a dozen of the other. But I kind of think it's more like 6 of one and 7 of the other, because 7 being the customer side of it. In my experience, they're often more likely to fail than the device itself. Okay, so do not discount the faulty customer, the faulty owner. They're everywhere, yeah, and you can waste a lot of time trying to diagnose them. To the point in the end, you just put your hands up and say, sorry mate, I can't do anything with this. Okay, so that is the last one. Hope you enjoyed this video. I hope you've learned some things. I mean, I've discussed quite a lot of the problems you're likely to see between the two videos I've made. I do believe if you watch this through, it will make you a better repair tech than when you started. And if I miss something important that you guys know about, well, you know what's down underneath me. It's called the comments, yeah? Get in there and let me know, whether it's praise or criticism. Hopefully constructive, but criticism. I want to hear from you. So let us know down there. Hope you did enjoy watching that video, and I hope you'll be back soon on Learning Electronics Repair. Ciao for now, guys.